So the difference between the final and initial volume will give you the change in volume, which is also equal to length into area. So how do you obtain the enthalpy? It is the sum of internal energy and the product of pressure and volume. So this is the equation. H is equal to U plus PV. Now there are two types of heat capacity we have to study here, that is molar heat capacity and specific heat capacity. Hello everyone, this is Ambali Unnikrishnan from the Department of Chemistry, Vidhyaashram School of Excellence, Mysore. So today we are back with session 3 of the chapter Thermodynamics. So in the last session we studied what is internal energy and change in internal energy of the system, as well as the first law of thermodynamics. Right. So in today's session we are going to study about the different applications of first law of thermodynamics. We studied what is first law of thermodynamics as well as the equation for it, right? So we are going to study the different applications of it. Thereby we will study the next concept, that is enthalpy, as well as heat capacity, and a very important relationship between Cp and Cv for an ideal gas. Okay. So what is Cp and Cv? All this we will study in this session. Okay. So now let us begin with the application. So now we are considering a cylinder which contains 1 mole of an ideal gas fitted with a frictionless piston. So as you can see here, we are taking 1 mole of an ideal gas here, which is attached with a piston. Okay, it is a frictionless piston, so we can press it or apply pressure there, right? Okay, so total volume of the gas is Vi and the pressure of the gas inside is P. Okay, so initially the volume of the gas which is present inside the cylinder is Vi. The volume is Vi. Okay, and the pressure is P initially. Okay, now what we are going to do is we are going to apply an external pressure, and if the external pressure we are applying, if it is greater than the pressure inside, what happens? If the external pressure is more, yes, the volume starts decreasing. That means, yes, initially it was here the piston, now the piston will be here. It will apply a pressure. Okay, so if P external is greater than P, what happens? The piston moves inwards till the pressure inside becomes equal to P external. So till what extent this piston will move inside? Till the P external and the pressure which is present inside, okay, this becomes equal. Till then the piston will move inwards, right? Okay, now let this change be achieved in a single step, and the final volume, let it be V final. So now the volume of the gas which is present here is Vf. Okay, so once more, initially it is the volume of the gas present here is Vi, right? Now we applied a pressure which is greater than the pressure of the gas which is present inside. Now that is P external should be greater. So what happens? The piston will start moving inwards. Okay, and it will move until this both becomes equal, and the final volume will be V final, right? Now the volume changes length into area, right? Volume is what it is, length into area, or else you can also write it as delta V. What is delta V? It is the change in volume. That means V final minus V initial. So the difference between the final and initial volume will give you the change in volume, which is also equal to length into area. Right. Now the force on the piston. What is the equation for force, or what is the equation for pressure? Pressure is equal to force by area. Pressure is the force applied in a unit area, right? So how can I write in terms of force? It will be force is equal to pressure into area, right? So that is what is written here. So the force applied by the piston will be equal to P external into area. Right. Now, if W is the work done on the system by the movement of the piston, okay, if W is the work done on the system, then how do we write W? The work will be equal to what? Work is equal to force into distance. Okay, work is equal to force into distance. Now, what is force? We already know it is P external into area. That is force. Okay, and the distance is the length. And we know area into length is what? It is delta V, right? So that is how you got this equation. That is work is equal to P external into delta V. Okay, so also you can write as P external into minus delta V. Now, why it is written minus delta V? Yes, as you can see here, delta V means what? It is V final minus V initial. So by seeing here itself, you can tell which one will be greater. Yes, V V initial will be greater than V final. So if we are taking V final minus V initial, you will get a negative value, right? That is why the negative sign here. So you can take the negative outside and write P external into delta V, or minus P external into V final minus V initial. So I hope it is clear, right? Till here it is clear. Now, there is an important note here. The negative sign of this expression is required to obtain the conventional sign for W, which will be positive. Now, what is this? Work done on the system. Yes, we are applying a pressure using a piston. So, work is done on the system or by the system. The work is done on the system. Hence, if the work is done on the system, yes, according to sign convention, the W must be always positive. Okay, that is why we are using a negative sign here, so that the negative and negative will get cancelled and you will get a positive value for the work. Okay, it indicates that in case of compression, work is done on the system, and here Vf minus Vi will be negative, right? And the negative and negative will get multiplied and you will get a positive. Hence, the sign obtained for the work will be positive. Okay. Right. So, I hope this equation is clear for you. Right. Now, moving on to the next one, that is called as free expansion. Okay. So, what do you understand by free expansion? So, it's the expansion of gas in vacuum. So, it is an expansion of the gas in vacuum. So, we can say that the P external will be equal to 0. Okay, and it is called as free expansion, and no work is done during free expansion. No work is done during free expansion for an ideal gas, whether it is reversible or a irreversible process. Okay, so what is free expansion? You have to remember, in free expansion, P external will be equal to 0 and there won't be any work done by the system. So the work also will be equal to 0 in case of free expansion. Okay. Now moving on to the next part, that is we are studying about the different applications of first law of thermodynamics. So we have studied the equation for first law of thermodynamics, that is delta U, which is change in internal energy, is equal to the Q plus W. Okay, so now we are going to write it in different number of ways depending on the type of processes which is happening here. So in the first session we have studied the different types of thermodynamic processes, right? So depending on the different types of thermodynamic processes, this equation for first law of thermodynamics keeps changing. So let's see. So let us substitute W is equal to minus P external into delta V. That is work done from this particular equation. We have obtained this, right? So the work done is equal to minus P external into delta V. So now this equation for W we are going to substitute in the first law of thermodynamic equation. So the equation becomes delta U is equal to Q, and in place of W you substitute minus P external into delta V. So you get this equation. Right. Now for different thermodynamic processes we are going to see. So if it is an isochoric process, so what is isochoric process? The change in volume will be equal to 0, or else you can say that the volume will be constant. So that means delta V is equal to 0. So if delta V is equal to 0, what happens to the equation? Yes, this P external into 0 will be 0, right? So what will be the only terms left? Delta U will be equal to Q, right? So delta V U will be equal to Q. For an isochoric process, delta V equals 0. So the first law of thermodynamics becomes delta U is equal to Q. Change in internal energy will be equal to Q. Right. Now next one, if it is for isothermal and free expansion of an ideal gas. So in the case of an isothermal and free expansion, what happens? W will be equal to 0 by P external is equal to 0. Right. Also the Q will be equal to 0. Hence what happens to the equation? Delta U becomes equal to 0. The change in internal energy also becomes 0 for an isothermal free expansion of an ideal gas. Now the last one is for an adiabatic process. We know that for an adiabatic process, Q will be equal to 0. There won't be any change in heat. Q will be equal to 0. So what happens to the equation? This term becomes 0, means delta U will be equal to W. So delta U will be equal to the work done in an adiabatic process. So depending on the different thermodynamic processes, the equation keeps changing for first law of thermodynamics, right? Now, for an isothermal irreversible process, what will be equal to 0? The change in internal energy will be equal to 0. So, the equation becomes, yes, this was the equation, delta U is equal to Q plus W. Now, this is 0. So, we take the W to the other side. It becomes Q is equal to minus of work done, right? So, Q is equal to minus of work done. We know already the equation for work done. It is minus P external into delta V. So, that minus and this minus will get cancelled and you will get P external into delta V, or else P external into V final minus V initial. This is for an isothermal irreversible process, right? Now, if it is an isothermal reversible process, yes, then we know that Q is equal to minus W. Again, Q will be equal to minus W because delta U is again 0. Okay, but if it is for the work done for an isothermal reversible process, we have already studied the equation. It is nRT ln V final minus initial. It is in ln terms. We can convert it into log also by multiplying it by 2.303. So, the equation becomes W minus W is equal to 2.303 nRT log V final minus V initial, or else in terms of pressure also you can write, that is W is equal to, yes, the negative was here, I can shift the negative here also. So, the equation becomes work is equal to minus 2.303 nRT log P1 by P2. So, either in terms of volume or in terms of pressure, you can write this equation. So, this is in the case of isothermal reversible process. So, in case of isothermal reversible process, the equation for work done is minus 2.303 nRT log V final minus V initial, or else in place of that you can write it in terms of pressure as well. Now, moving on to the next important concept, that is called as enthalpy. So, we have already finished what is internal energy and change in internal energy, first law of thermodynamics and different applications of that. So, let us see how enthalpy is defined as, which is represented by the symbol H. Okay. So, enthalpy of a system is defined as the total heat content of the system. So, it is the total heat content of the system. So, what is enthalpy? It is the total heat content of the system. And how can you obtain the total heat content of the system? It will be the sum of internal energy. Okay, it will be the sum of internal energy plus the product of pressure and volume. Okay, so how do you obtain the enthalpy? It is the sum of internal energy and the product of pressure and volume. So, this is the equation. H is equal to U plus PV. This is the equation of enthalpy. Again, what is enthalpy? It is the total heat content of the system. Now, enthalpy depends on quantity of the substance and on the state of the system. Hence, it is a state function and an extensive property. Okay, as it depends upon the quantity of the substance and on the state of the system, it's a state function as well as extensive property. So, we have already studied what is extensive property and intensive property. Intensive property is independent of mass and extensive property depends on mass. So, enthalpy is a quantity which depends upon the mass. Okay. Now, next is change in enthalpy. So, the same equation, if I am writing in terms of change, okay, change in enthalpy, delta H will be equal to delta U plus P delta V. P delta V. Delta H is equal to delta U plus P delta V. That is, change in enthalpy is equal to change in internal energy plus pressure into change in volume. So, we have already studied what is ideal gas equation, that is PV is equal to nRT. Okay. So, in terms of change in volume, how do we write? It can be P delta V is equal to delta Ng RT. Okay. So, this P and delta V comes here and delta Ng RT. Now, what is delta Ng? We know N stands for the number of moles. Now, what is delta Ng? Yes, it is the number of moles of gaseous products minus the number of moles of gaseous reactants. Okay. So, that is why this G you can see here. It is only the number of moles of gaseous products minus the number of moles of gaseous reactants. Only in the gaseous states the products and reactants are there. The difference in number of moles of those gives the value delta Ng. Okay, so instead of, see, we know that P delta V is equal to delta NGRT. So this P delta V I can substitute in this equation. So the equation becomes delta H is equal to delta U plus delta NGRT. So instead of P delta V I can even substitute that. So this is another equation for change in enthalpy. Right, okay. So I hope delta Ng, what it is, also clear for you. It is the difference in the number of moles of gaseous products and gaseous reactants. Now, for solids and liquids, the term pressure and volume are negligible. So, in the case of solids, pressure and volume are negligible. So, what happens to the equation? It is just the enthalpy and internal energy. So, what the equation becomes? It becomes H is equal to U. The P delta V or PV term is neglected. Now, in a chemical reaction, change in enthalpy is given by delta H is H of the products minus H of the reactants. So, in a chemical reaction, reactants gives products, right? So, the change in enthalpy will be the enthalpy of the products minus enthalpy of the reactants. Now, enthalpy of an element is assumed as 0 in its standard state. If it is in its standard state, okay, the enthalpy is considered as 0. Now, delta H is equal to QP, okay, that is heat absorbed by the system at constant pressure. So, this is a very important equation. Delta H, the change in enthalpy, will be equal to the heat absorbed by the system at constant pressure. That is why you can see the P here. Delta H is equal to QP. Right. Now, delta H is negative for exothermic process which evolve heat during the reaction. So, delta H will be a negative value if it is an exothermic process and delta H will be a positive value if it is an endothermic process. And at constant volume, what happens? Delta U will be equal to QV. Therefore, the above reaction will become, the above equation will become as delta H is equal to delta U, which is equal to QV. Okay, so we studied that delta U is equal to heat absorbed by the system at constant volume. We already know this. Delta U is equal to QV. And we know that delta H is equal to delta U and which will be also equal to QV. Right. So, I hope it is clear. Now, moving on to the next one, that is heat capacity. So, we completed enthalpy and the change in enthalpy and the different equations for it. Now, next one is heat capacity. Now, the increase of temperature is proportional to the heat transferred to the system. That is, the increase in temperature is directly proportional to the heat transferred by the system. Okay, so temperature is directly proportional to the heat transferred by the system. So, that means the heat is directly proportional to the temperature, and to remove the proportionality constant, you can write Q is equal to constant into T. Now, this constant is called as the heat capacity. Okay, so now that constant is called as the heat capacity. So, the equation becomes Q is equal to C into delta T, where Q is the heat and C is the heat capacity and delta T is the change in temperature. So, Q is the heat is applied to the system. Okay, and delta T is the increase in temperature and the coefficient C, right? The C is called as the heat capacity. Okay, and the magnitude of the coefficient depends on the size, composition and the nature of the system. So, it depends upon the size and the nature of the system. So, this is called as the heat capacity. So, it is Q is equal to C into delta T, and where C is the heat capacity of the system. Right. Now, there are two types of heat capacity we have to study here, that is molar heat capacity and specific heat capacity. So, first let's begin with the first one. Molar heat capacity is defined as the quantity of heat needed to raise the temperature of 1 mole of substance by 1 degree Celsius or 1 Kelvin. Okay. So, it is the quantity of heat. It is the quantity of heat required to raise the temperature of 1 mole of substance by 1 degree Celsius. So, molar heat capacity is the quantity of heat which is required to increase the temperature of 1 mole of substance by 1 degree Celsius. And the next one is specific heat capacity. It is defined as the quantity of heat required to raise the temperature of the system by 1 degree Celsius again, but it is for 1 unit mass of a substance. Here it is 1 mole of a substance and here it is 1 unit mass of a substance. So, that is the difference between molar heat capacity and specific heat capacity. So molar heat capacity is to increase the temperature of 1 mole of a substance, how much heat is required, how much quantity of heat is required, and specific heat capacity is the amount of heat required to raise the temperature of 1 unit mass of a substance. Right. Now, we are going to study about the relationship between Cp and Cv for an ideal gas. This is a very important relationship. Okay. So, what is Cp and Cv? We already know what is C. C is the heat capacity, and heat capacity is constant pressure is Cp and heat capacity at constant volume is Cv. So, let's see. At constant volume, the heat capacity is denoted as Cv, and at constant pressure, the heat capacity is denoted as Cp. So, we can write the equation for heat at Q at constant volume. Q at constant volume is equal to Qv. Right, Qv, which is equal to Cv into delta T. Just now we have studied this equation for heat capacity, that is Q is equal to C into delta T. So, if you are considering Q at constant volume, this becomes Qv and C will become Cv and delta T will be delta T itself, right? And Qv is equal to delta U. We already know that Qv is equal to what? Delta U. Okay, so this equation is like this. The next one is Q at constant pressure. Okay, and heat at constant pressure will be equal to Cp into delta T, which will be equal to delta H. Okay, again, if it is Qp, the equation becomes Cp into delta T. And we have already studied this. What is Qp? Heat absorbed at constant pressure, that is equal to delta H. Heat absorbed at constant volume is equal to delta U. So, those are these two equations. Now, for 1 mole of an ideal gas, delta H is equal to delta U plus P delta V. We have studied this. This is the equation for change in enthalpy. Now, substituting P delta V by RT. Okay, so we know that PV is equal to nRT, right? So, instead of PV, we can substitute RT, right? So, the equation becomes delta U plus delta RT, and if we take the delta inside, R is a constant value, right? So, it becomes delta U plus R into delta T. Okay, so the equation becomes like this. Delta H is equal to delta U plus R delta T. Instead of P delta V, we substituted R delta T. We got that equation from the ideal gas equation. Now, substituting the values of delta H and delta U. Now, in this equation, we are going to substitute the values of delta H and delta U we have calculated in the beginning. So, the equation becomes Cp into delta T becomes, that is delta H is equal to what? Delta H is Cp into delta T. So, Cp into delta T will be equal to, what is delta U? Cv into delta T plus R into delta T. Okay. So, now delta T is common here. So, we can cancel it. So, the equation becomes Cp, Cv and R. That is the only terms which is remaining. So, Cp will be equal to Cv plus R, or else I can write Cp minus Cv is equal to R. So, from this equation, that is delta H is equal to delta U plus R delta T. In place of delta H, I substitute Cp into delta T. And in place of delta U, I substitute Cv into delta T. And what else is remaining here? R delta T. So, delta T gets cancelled. What is remaining? Cp is equal to Cv plus R, or else Cp minus Cv is equal to R. Just taking the Cv this side. So, this is the relationship between Cp and Cv. That is heat capacity at constant pressure and volume. The difference of that will give you the ideal gas constant. So, the difference between Cp and Cv will give you the gas constant. Cp minus Cv is equal to R. So, Cp minus Cv is equal to R. This is a very important relationship. Okay. So, I hope the relationship between Cp and Cv is also clear for you. So, in the next session, we are going to study the measurement of delta U and delta H. That is change in internal energy and change in enthalpy. So, I hope in today's session, the topics we have discussed is clear for you. So, that's all for today. Thank you.